Dear friends, today I will be discussing on stability of an aircraft, right? And remember, we have already discussed this at length, and today is the session where we will revise, revisit, and try to understand what is the meaning of a stability of an aircraft. And as you recall, when you talk about stability, what comes to your mind? Yes, can you tell me, any student, what comes to your mind when you think of stability? Go to class 10th, 11th standard.
When everything is balanced and everything is equilibrium, all the forces and moments are equilibrium.
See, when all the forces and moments are balanced, we say that is equilibrium, right? Not really, we talk about stability.
Lowest energy state.
Pardon?
Lowest energy state.
Yeah, that is another, yes. That is again equilibrium when you talk about energy state, right? And if you...
Whether the object can reback into...
Yes. So, as I was telling, if you think of your school days example, remember this sort of a diagram. So if I displace this body from its equilibrium, this is the equilibrium, okay? Where you are telling all the forces, moments are balanced. If I disturb this from this equilibrium, and if it has initial tendency to come back to equilibrium, we say statically stable, correct? Okay. For example, if again we revise, if there is a mass spring system, and if I stretch it and release it, the moment I stretch it, there is a force trying to restore, so it has an initial tendency. The key word is initial tendency. To come back to equilibrium, okay? Now for aircraft, this is the aircraft. If say this aircraft is flying at an alpha equal to 2 degrees, what do you mean by static stability? Suppose it is flying at an angle 2 degrees, and because of some upward gust, the angle of attack is increased. So if it is statically stable, it should generate nose down moment, so that net angle still remain 2 degrees. So as static stability, we only check whether it has got a tendency to come back to 2 degree or not. If it has a tendency, you say it's statically stable. And this nose down moment, you all know this sign is negative, and nose up moment sign is positive. And you are also aware of this term Cm, which is pitching moment, half rho v square s c bar. So what do you say is, if this is Cm and this is alpha, the variation of Cm with alpha should be like this. What is the equilibrium point here? The equilibrium point is here because here Cm is 0 and net force is also balanced. It is typically like your airplane is cruising, okay, where thrust equal to drag, lift equal to weight. Now if you want to check whether this is statically stable or not, what you should do? You should give a disturbance about the stream point. So let's say the airplane suddenly its angle of attack has increased. So what this diagram is showing you, if the angle of attack has increased, immediately it will generate a negative pitching moment. So it has the initial tendency to come back to this angle. Correct? So we say this is statically stable, and mathematically we say Cm alpha less than 0, or if I write more explicitly, dCm by d alpha less than 0. Correct? Now also we checked this issue that not only the slope, but another important point. Suppose I draw it like this, and this is Cm and this is alpha. This is the trim point, Cm is 0. Here also the slope is negative. So which one you will prefer, this one or this one? Why first one? Yes?
Have the value for Cm even when alpha is equal to 0.
Yes. Very good. I would express this like this. Finally, when I'm going to fly a machine, I want angle of attack should be positive, so that there is a lift. As well as it should fly like this. It should not go on doing like this. So Cm should be 0. It should fly like this. So I'll try to see that this not only should be stable, that not only dCm by d alpha should be less than 0, but also it should, this is called trim, okay? Trim at positive alpha, correct? To ensure that trim is at positive alpha, the graph should look like this. Or what you are telling, Cm at alpha equal to 0, that is, I write it Cm naught should be greater than 0. Correct? If you satisfy these two things, then you can fly a machine which is stable, statically stable, right? You also know this Cm, whatever the pitching moment is coming, this contribution will come from wing, it could come from tail, it could come from fuselage, it could come from landing gear, right? Because all will generate forces and that will give moment. And this Cm, we should remember, this is about center of gravity, because a body in free space will rotate about an axis passing through center of gravity, right? So all these Cm or the moments are about center of gravity of the airplane. Now see, this is very important. If I see the wing part, okay? What is my aim? My aim is dCm by d alpha should be less than 0 of the whole airplane. I like to check what is dCm by d alpha contribution because of wing. Correct? Now, if I see a wing and there is an aerodynamic center, you know what is an aerodynamic center? It is the fictitious point about which the pitching moment is independent of angular attack. And let's say CG of the airplane is somewhere here. So if I draw it explicitly, this is the wing, and this is the, typically this is at quarter chord, and this is the CG of the whole airplane. Because we are talking about Cm about CG of the whole airplane, right? Now, do you think this will give dCm by d alpha negative? Check yourself. If there is a disturbance, say alpha, then I will represent the force acting through AC. So AC is here, and CG is here. This force or delta lift will give what type of moment? Will give positive moment about CG. That means for positive alpha, you have got positive moment. So this is telling dCm by d alpha is greater than 0. So this is a destabilizing contribution. Clear? How do you make the same wing having stabilizing contribution? You have to ensure that I lay the wing in such a way that if this is the CG of the airplane, if I put the wing in such a way that AC is behind CG of the airplane, it will give stabilizing contribution. So what is the lesson learned? If I want from wing, if I want dCm by d alpha negative, then AC of the wing should be behind CG of the aircraft, correct? But we know very well, it is not only we are looking for slope here, which is dCm by d alpha, we are also looking for this gentleman, Cm naught should be positive. And let us see if I put the wing the way we realized to get stability, whether Cm0 contribution is positive or negative. If this is the wing, this is a cambered wing. If this is the AC of the wing and this is the CG of the wing, you know when we have a cambered wing aerofoil, we have got CmAC of wing which is less than 0, right? Typically minus 0.02, minus 0.1. It will be there because we are transferring the forces and there will be a moment here. But now if you want to calculate Cm0 because of wing, what will happen? At alpha equal to 0, there will be a force CL0 or non-dimensional CL0 acting at AC. This is okay or not? Because you know for a cambered aerofoil, something like this CL0, right, at alpha equal to 0. What this CL0 will do? At alpha equal to 0, this CL0 will give what type of moment about CG? Nose down. Negative moment. So what will happen? You have already CmAC of the wing. Now you will have the CL0 into x bar, which is also negative. Let's say I say this distance is x bar. So overall Cm0 because of wing is becoming what? Negative. This is negative. This is also negative. But what we are looking for? We are looking for positive. So we are not happy about it. Right? So what is done in most of the aircraft, you will see that AC of the wing is actually kept ahead of CG. So the wing is destabilizing, number one. However, it gives relatively positive Cm0. If you see here alpha equal to 0, there is a CL0 here. That will give a nose-up moment. Correct? You can check any aircraft which have a cambered aerofoil. Then the debate comes, what is the use of that wing which will be destabilizing the airplane? The answer is, stability is not the role of the wing. Primary role of the wing is what? Lift. Stability, somebody else will take care. Who is that gentleman who takes care of stability? It is the stabilizer, not the control surface. It is the horizontal stabilizer. Control surface takes care of the control. That is, I am flying at a particular CL, I want to go to another CL, so that is through control. That is not stability. This distinction should be there very clearly. And then if we need to know what is the elevator deflection for a particular CL, we again come back here. So this Cm versus CL, we agreed that here Cm is 0, which is a trim, that I am flying at this CL, and slope is negative, so statically stable. But suppose I want to fly at this CL, say CL star. If I try to fly at this CL, what will happen? See that immediately the airplane will generate a negative pitching moment. So it will not allow it to go to that CL. That means if I want to increase CL, I have to bring the angle of attack up using elevator. But because it's statically stable, it will generate a negative moment. So if you want to fly at this CL, what do you have to do? You have to ensure that this negative moment is nullified. And who does it? That is the control part. That is done by the elevator. This is your tail, okay? This is the elevator. This is CG. Now, suppose you want to fly to another CL star as a trim. The airplane generates negative pitching moment. So the airplane tries to come back like this. But you want to hold it like this. So what do? You put the elevator up. Okay? As you do elevator up, net force here acts downward, right? And this will give a positive moment, and you should carefully deflect this elevator up such that this magnitude of negative moment is nullified. then you are flying at a different CL. And this is the control part. This comes through the elevator. Okay? And how to approach this problem? That is given by what is the Cm? You know, Cm is Cm naught plus Cm because of Cm alpha into alpha because of angle of attack, and Cm delta E into delta E. These are all, this is coming from stability, right? This is coming from control. So if I have got an aircraft where Cm delta E is very strong, then I should be able to easily control the airplane. Okay? This is one, and you must be doing this. If I try to plot delta E required for different CL trim, the variation is like this. Here again, you could see that if I am flying at this CL trim, if I want to fly at this CL trim, this variation will tell you how much delta E negative you have to put. So this directly gives a feed to the pilot. Before he goes for a flying, he will check what are the elevator deflections, and that's why he trains himself. Now imagine if I go on taking the CG of the airplane backward. What will happen? See from here, you know, if I take this CG backward, there will be a time when CG and AC will coincide, so it will become neutrally stable. So there is a neutral point concept of the whole airplane. There is a location at which if I put the CG, the airplane becomes neutrally stable. Beyond that, if we take the CG, it becomes statically unstable. Let us come back to stability. Suppose I have an airplane where the wing is high wing. Okay, and tail could be somewhere here. This is typically configuration of which of the airplane is high wing airplane in flight lab? Cessna 206, which are, right? The question is, we are very much clear about Cm versus Cl. We want this slope should be negative at trim, and we need to know about Cm naught at alpha equal to 0. Suppose the wing is high wing, another case the wing is a mid wing, another case let's say wing is a low wing. Okay, and CG is somewhere here, or somewhere here. Or to make the problem simpler, I say CG is somewhere here. Now check from stability point of view, high wing versus low wing in longitudinal case, that is what we are discussing. Which one is more stable? That is the general confusion. High wing is more stable in lateral directional mode, but we are talking about longitudinal. So you can, do you understand what is the catch? See here, if there is an increase in CL because of a disturbance, suppose here, CL has suddenly increased, that means suddenly angle of attack has increased because of gust or because of anything. Then what will happen? This CL of this wing will increase. CL means, you know, drag polar, CD equal to plus KCL square. So what will happen? If CL increases, CD increases. The CD will act in this direction, right? So this will give what type of moment about CG? So this will contribute to, so this is destabilizing. Please remember, for longitudinal case, the high wing is destabilizing. For lateral case, it is stabilizing. Similar thing you can check here. If there is increase in alpha, as here, the drag will be, additional drag will come here. This will give what type of moment? About CG? Nose down. So low wing will be providing static stability in longitudinal case. Is this part clear? So let us take another case. If this is the airplane, and let's say landing gear is out. Okay, flying like this. If I draw Cm versus Cl, where landing gear was in, that is inside the fuselage. Now you have ejected the landing gear out. How this graph is going to change predominantly? Cl is okay, Cl remains same. You should think like this, what is happening to this Cm naught? So what is Cm naught? Cm naught is Cm at alpha equal to 0. So if alpha is equal to 0, then this will experience a drag. What we are trying to compare is, suppose the airplane is flying with landing gear in and then landing gear out. Typical landing gear out will be during landing. Okay? And we are saying when the landing gear was in, Cm versus Cl was like this. When the landing gear is out, how the Cm versus Cl as a designer should think will going to change. So best way to think is first check what will happen to Cm naught. See at alpha equal to 0, this landing gear will experience a drag. This drag will produce a nose down moment, negative moment. So Cm naught will decrease. Is it clear? Everybody? So now Cm naught will come somewhere here. And as far as stability is concerned, you know drag means what? It is half rho v square s cd. For cd I write cd naught plus k cl square. Can I write this? No, I cannot write this because this drag polar is for wing. Right? This is not this, whatever form is there, this is for wing, lifting body. So I will not commit this mistake of writing like this. However, I will know one thing, this CD, I can write it as CD, some CD naught plus CD alpha into alpha. That means there will be change in CD because of alpha. That much I can approximate. So you could see since the alpha is there, whatever moment this drag is giving nose down will have a alpha component. So the slope of moment because of drag also will be negative now. Whatever moment is what? Moment will be d into whatever length, okay, jet CG, correct? And d is half rho v square s CD naught plus CD alpha into jet CG. But I have to ensure that I put a minus sign because I know with alpha naught, alpha equal to 0, this will give a nose down moment. So if I find dm by d alpha, so this alpha is here, I will get a negative sign. So this will make the airplane little more stable. So we will find that this slope at this point will be more than the slope here. So basically landing gear is changing the Cm naught. However, marginally it may increase the static stability, correct? Again, if I see this is the airplane, let's say Cm versus Cl is like this, and if I put another surface here, that is, I put a canard here, how this graph is going to change if I assume that CG has not altered? How this will change? It will become more stable or less stable? So the best way to check is always if this is the CG, any component which is ahead of CG will be destabilizing. You have checked that, no? If AC is here and CG is here, then only it is statically stable. If AC is behind CG, but this is AC of this component is ahead of CG. So this will make it less stable. And that is why when you want to have a maneuvering aircraft, you will find a lot of canard surfaces are used. So stability is reduced, so I can turn faster rate. We were discussing about stability for long, and we were very emphatic that wing's primary role is for lift, but we'll see in a secondary manner, wing also supports stability or it may contribute to static instability. This is Sinus 912. This is also high wing aircraft. And now when I am talking about static stability, suppose this airplane was flying at a angle 1 or 2 degrees, and there is a upward gust and the additional angle of attack is coming like this as a disturbance. The moment there is an additional angle of attack, there will be additional drag because it comes through the drag polar. And the additional drag, which will be acting towards this, towards the tail, in that direction, this will give a nose-up moment about center of gravity. So high wing is not preferred as far as longitudinal stability is concerned. You will see high wings are in demand for lateral directional stability. And that is why you will find why there is a high wing, why there is a dihedral. But theoretically, fundamentally you should know, although high wing is adding towards lateral or directional stability, which will be coming later, but high wing in particular adds to instability of the airplane, okay? Because this drag, through drag it operates. And if you now come to the engine side here, now we are thinking or discussing, which already have discussed in the classroom, what happens, what is the contribution of this propeller on the longitudinal stability of the airplane, especially static stability. And you know, if there is an angle of attack disturbance coming here, then there will be thrust will have a direction like in this way, and there will be normal component of thrust which will be function of angle of attack in a loose way, and this will give a nose-up moment about CG. So such nose-mounted engine, whether it is a propeller-driven or whether it is jet engine or duct-based, they all, if they are ahead of CG, all such engines, if they are located ahead of CG, will contribute to instability of the airplane as far as static stability is concerned. Right? Same engine, if I put behind CG like a pusher, then they will contribute towards stability, static stability. So wing, this is the propeller, horizontal tail already you know, landing gear we have discussed, and that makes the whole understanding of static stability. That also makes us understand who contributes what. To conclude, we see that horizontal tail primarily contributes to a longitudinal stability, and wing has a marginal effect. High wing will contribute towards instability in terms of static configuration concern. And if you see this wing, which is a low wing configuration, so this will actually add to static stability, okay, in terms of longitudinal stability. We will discuss their effect on lateral or directional stability in lectures coming ahead. Okay. Thank you very much.